Alrighty, today's topic, an exciting one at that, is photoelectric effect. Photoelectric effect. So a while back there was a scientist, little known scientist, he wasn't that big of a deal. His name was Albert Einstein. Just a little guy, Albert Einstein dude, alright? Obviously, guys, Albert Einstein did a lot of things in physics, did a lot of things in science. And a lot of people think that Albert Einstein is famous for this. E equals mc squared. And he is, okay? He's very famous. However, Albert Einstein won a Nobel Prize in Science. He didn't win it for E equals mc squared. You know what he won it for? Photoelectric effect. It's a pretty in-depth concept, but I think it makes sense as we explain it. So we're going to be doing some drawing, we're going to be doing some visualization, that kind of thing. So right now I want you guys to go like on a journey with me in your brains, okay? So it is the first day of football, like August 15th, okay? And you know, were lucky, your parents just bought you a fully loaded black Mustang. We're talking black leather, black interior. This thing is sweet.
I would cry.
All right? I mean, you are living the dream, you know, riding back in your Mustang. All right? You're having a good time. So you show up 8 a.m., first day of practice. The forecast, 100 degrees and pounding sun. Okay? You go to football practice, you go to get in your car at 2:30. Remember, your car is black. I mean, black leather, black everything. Black paint, black interior, whole thing. So you go to sit down in your car, what happens? Ooh, that hurt a little bit, right? Okay. You go to grab your seatbelt, and you're like, ooh, I just like scarred my hand, right? So your car is really, really hot. You know why your car is hot? Photoelectric effect. So let's explain it. At this time, so cars are made of what metal? Do you guys know? For the most part. Steel. Steel is an alloy, and a large part of that alloy is iron. So what I'd like you to do is take a minute right now and draw me the atom for 56Fe. So that's the isotope you have. Draw that atom. Alright, so the atom we have right here is iron. 8 valence electrons. The reason is because, how many electrons fit the first level? 2. Come on, talk to me. How many? 2. 2. How many in the second level? 8. How many in the third level? 8. And then 18, right? Well, these numbers mean something to us. Some of us are still struggling a little bit with this, all right? Remember, we have a mass number and an atomic number. The atomic number I had to go get from the periodic table. The atomic number tells us two things. The protons and the electrons. The difference between them, 56 minus 26, is the neutrons. On our quiz, I would say about 95% of us have this down. But the fact of the matter is, I want 100%. I want everybody on the train. Okay?
I fell off the train.
Well, then get back on it. We don't want trains running people over. It's just not a pretty sight. So, 26 electrons here. 2, 8, 8 made 18. And that's where you get 19, 20, 21, 22, 23, 24, 25, 26 for 8 valence electrons. Now, here is the photoelectric effect. We said yesterday, like 5 minutes ago, that it was a really, really nice day outside, meaning the sun was blazing. So the sun is blazing down on these atoms of, technically, I guess it's alloy of steel. But for now, we're just going to talk about these atoms. So, the sun, we call this radiation. And what happens is radiation is being exposed to these atoms. Now, when you guys go to the beach in the summertime, or even when you go like on your spring break trips, right, make good choices along the way and all that good stuff, okay? You know, you go sit on the beach, right? What happens to you?
You burn.
You get, okay, you're fried, but you warm up, don't you? Electrons, they do the same thing. They capture energy. So what happens is, if I was an electron, all right, you know, 8 o'clock, I'm warming up, 9 o'clock, 10 o'clock, 11 o'clock. I mean, I'm really jacked up now. Right? You know, it's 1 o'clock, okay? I mean, I am really excited. And eventually what happens is this. Normally, atoms are in what we call their ground state, meaning you're on the ground. Everything's just normal. But what happens is radiation happens, and this electron, let's pick this one right here. What happens is it gains energy, 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 and it jumps up to another level.
Oh my God, I thought you were going to die.
Okay? So now it gets up here, and it's still really, really riled up. All right? This is called the excited state. And you're excited, you're excited, you're excited, you're excited, you're excited, you're excited, and then that source of radiation begins to dissipate. And begins to dissipate, and begins to dissipate. And what goes up must come down. So this thing starts to lose its energy, starts to lose its energy, starts to lose its energy, and falls back to its ground state. Okay? Yes?
Okay, so only electrons. You know.
That is correct. It is the electrons, because remember, these things are inside of the nucleus. The electrons are the volumes. They're on the outside. So the electrons jump. Now, guys, they can jump 1 level, they can jump 2 levels, they can jump 3, depending on the source of radiation. Was that what you were going to ask out? It depends. And what goes up must come back down. So here, we have something going from its ground state to its excited. So up here, it's excited. It doesn't belong up there. And back in here, right, is its normal. It's ground. Now, we know something about energy. Lavoisier says that energy is what? Recycled or conserved. So guys, does this energy, is it just lost? Is it just gone? Is energy lost? No, it just changes form, right? So what happens is this. You have this energy that's right in here. This energy leaves. This energy is released to its surroundings. And that kind of energy, or that amount of energy, is called a photon. So we make photons of energy. Now here's the last thing that ties together this whole photoelectric effect. Okay? This photon of energy. How do I know it happened? Because you see it as light, or you feel it as heat. And that's why your car, on that 100-degree day, first day of football practice, right, feels like it's going to burn you. Because what happened is all day long, that steel, whatever's inside the atoms in the leather, whatever, was undergoing photoelectric effect. It was ejecting electrons, and then when those electrons were ejected, that energy had to go somewhere. It was a photon of energy that we see as light or feel as heat. And guys, that idea, radiation, ground state, excited state, back down, energy released as a photon of light or heat, is called the photoelectric effect. Alrighty, let's build on this now. So we talked about this photoelectric effect, right? Source of radiation causing electrons to be excited, falling back down to their ground state. Energy being released as a photon, felt as heat or as light. Do you remember this guy? De Broglie.
Yeah, that guy.
Because de Broglie had a little thing known as wave-particle
Duality.
duality. here's where wave-particle duality happens. You ready? These things in here, the protons, the neutrons, and electrons, are called subatomic particles. So, particles cause photoelectric effect, don't they?
Yeah.
But here's the part that's right here. Heat and light. Do you know why we interpret heat and light? It's because these things leave as energy in the form of a photon. You know how they get from there to your eyes? They get there in the form of a wave. So, particles cause this to occur. And how do you know it? You know the heat or light occurred because your body is interpreting the different waves. So de Broglie, light exists as both particles and waves. There's the glue.
So is it like a wave of particles?
What's that? The particles cause the waves.
I see.
If there wasn't particle movement, if there wasn't this excited and ground state thing occurring, right, then you couldn't have these photons created. Right? And if these photons are created, then your body can interpret the light or the heat coming off of them because there's no waves. Okay? Alright, so let's continue in your packets now. Let's talk about waves a little bit. I'm going to try to stay in the middle, so unfortunately I got to go like that.
I didn't.
So let's talk about the characteristics then of what makes up a wave. Because light exists as both waves and as particles, right? So, wave.
I did it.
Here's an example of a wave. And I'm not, you know my artistic ability.
Should this be in our packet?
This is what you want to write for number 2. So you can work right in your packets right now. Here's the 0 point. Okay? Let's talk about some of these characteristics of waves. Okay? And I want this to be a wave that would keep going and going and going. Everybody know the term we give to the height of the wave? It starts with an A.
Amplitude.
It's called the amplitude.
Good job, ladies.
Thanks.
Amplitude. True or false? It's also the depth of the wave. The word amplitude.
True.
Yeah, so it's this too. So we can look at the height or the depth, either one. Now, when you're, surfing, right? Yeah, Pacific Ocean, Atlantic Ocean, wherever you go for spring break, making good choices, of course. You're going to be right on the top of that wave. What's the name of the very top of that wave? It starts with a C.
Crest.
Crest. So the very top of it is the crest.
No, he did.
Now, the very bottom of a wave, and the lowest point also has an A. It's not a crest. It's called the trough.
How do you know these things?
Okay? So we have a crest and we have a trough. A couple other things I want to point out to you. So, wavelength. When I hear that word, I break it up into 2 things. First of all, the first part is waves. So you're talking about something like this. And length says how long is it? Here's the thing about wavelength. Wavelength is measured by looking at adjacent points on a wave, meaning the same part. So, if I want to, I can keep it real simple. Since my wave started at the 0 point, went up, down, and came back to it, from here to here can be measured as one wavelength, or one wave. So this is wavelength. Does this color show up on the film?
Sort of.
That's
Are you
okay.
filming right now?
I am. I've only been doing it all hour. So,
All hour.
wavelength, all right?
Fair.
So, from here to there. My question to you is this. What if instead of wanting to measure it from the beginning, or the 0 point, I wanted to do it from crest to crest? Is that still the wavelength? Yes. All that matters, guys, is that I pick adjacent points. I believe you have a question next that says, what is wavelength then? I would draw a wave and demonstrate this. Okay? The idea that wavelength is from an adjacent point. And you can choose it. The 0 point to the 0 point, or the crest to the crest. You can do it from trough of this one to trough of this one.